Hello guys, how y'all doing? This is the last lecture of the midterm, and this is supposed to be to be honest, like the shortest lecture. I don't think this is that long of a lecture. And it's things you've already done before. We're just implementing it here this time. Okay? So let's head right into it. So last day we talked about, or last lecture, last lesson, we talked about finding the rate of change at any given direction. So you see, we find the rate of change, right? So this is our rate of change, our gradient, right? At any given direction, and we did the dot product with our u, and so we gave it the direction, we times it by our gradient, and it gave us the rate of change, rate of change in the direction. Excuse my writing. Rate of change in the direction of u, right? Now, what if I want to give it a point? So let's say we're here. You see this graph? Let's say I am right at this point. Okay, so I'll change the color. Let's say I'm at right at this point. If I want to find, instead of me giving it like, oh, I'm walking this way or I'm walking this way of the mountain, I want to tell you know what? I want to get up the mountain. Find me the fastest way, the steepest point I can go, which is usually straight up, right? And so what I'm asking is, I'm not going to give you a direction. I'm just going to give you a point where I'm standing and tell me what is the steepest, where the slope is the highest. So, like when let's say I have a 2D function now, and I have like this, and I tell the function, find me my steepest. So you see here, it's not steep, but right about here, this is very steep. And so I just give it this point, and it will tell me, oh, your steepest is straight up, right? So which direction produces the largest rate of change? So now I'm not giving it a direction. I'm giving it the rate of change. I'm giving it a point. I'm telling it now, give me the direction instead. All right. And so it's not necessarily direction. It still gives you the highest rate of change, but direction wise, the way it would work is we would take the magnitude of our rate of change. So whatever our rate of change at the point is, okay, and we times it by the magnitude of our u. And remember from last lecture we said u is just 1, right? Your u is just 1, so this goes to 1, and then cos your theta. This will give us my the largest rate of change. The question is, what is my theta? Which direction produces the largest rate of change? So your direction rate of change is by default on the highest. So you see here, my default, if I give my rate of change this point, by default it will point to the steepest. That's by default. Then what we used to do is we used to multiply by the direction to get our rate of change in that specific direction. So this goes to 1, and when cos is 0, when my u is also in the same direction, so the angle is 0, my theta equals 0. When I'm perpendicular to the rate of change, it gives me my largest rate of change, because by default this points to the largest rate of change. So if I give it a direction, it'll give me the rate of change in that direction. But if my direction is the same path as the rate of change, it gives me the largest rate of change. And so this also goes to 1 because it's 0. Cos of 0 is 1. And so what we say is your rate of change, your largest rate of change, your largest range, your largest, what was I saying? Rate. I don't know, I said range. Rate of change. Okay. Your largest rate of change is, upside down, is your direction rate of change at given point, at your x and y that you're looking for. All right. And so see, it says here, suppose f is differentiable of two variables. The maximum value of the directional derivative is, you would take your normal function, you would get your direction rate of change, which is your direction rate of change of x and y, is equal to the derivative of x and your derivative of y. Okay? So now we'll write a summary down here, is that max rate of change equals to your directional rate of change at the points you want. So all you do is you sub in the points into this directional rate of change, and your directional rate of change equals to your... So what do? First you derive in terms of x, then you derive with respect to y, then you sub in your points, and that is your max rate of change. Now, if asked for the direction of the rate of change, not necessarily direction, but if asked, let's see, max or rate of change in certain direction, what you do is you take your rate of change that you find up there, you take whatever you find up here, and you cross product it. Somebody keeps calling me. And you cross product it by your u. All right, that's how you get the rate of change in a certain direction. All right, trying to think what else is there. Direction rate of change. Okay, that should cover it. If you see, so this is like a contours map. Like, you know how we would have, like, you have your x, and I want to find a way to make this like get a line faster than that. But anyways, so you know how some contour maps, like we had, would be like circles in red and yellow like this, and we also had like some of them that would look like that. Does this ring a bell, guys? Contour maps, if you don't know, search it up. You should already know this. One example we also went through was circles like these, and then we had contour maps, and then you had like some equations that match. This right here is a contour map. And the way you could read this, each circle, you see this circle, your z-axis is the same along the circle. So if I had a mountain, so if I had like a mountain, all right, and imagine I am looking at the mountain from the top. So I will have this as my z, and I will have this as my z, which is different elevations, right? This is some point z, like 1.2, let's say. This is 1.3. Each circle is the same height, like 1.2, and then the second circle is 1.3. All right, and so what this says is, it tells you, you see, when they're compact, it says you can go from this height z to this height z fairly quickly because the distance is so small. But when you go from here all the way to this point, it's this z point is the same as this z point, and this z point is the same as this z point, because it's the same circle, right? For these two circles. But the time it takes you to get there, the rate of change between this and this is lower than the rate of change between this point and this point. And you can see that by how compact these layers are. You get from one layer to the other quite quickly, while here you get from one layer to the other quite takes a while. And so that's like going from, so if we have like a hill, and then we have like, so you see the change from here to this point on my x is pretty short, but the change from this point to this point on my x is pretty long. And so that's how compact it is if you look at it from above, right? So I hope that explains it well. Now let's consider graphically. I'm pretty sure we went over this. Okay, so find the maximum rate of change at a point. Now, how do we find the maximum rate of change? Remember how we said here, maximum rate of change, you just do this and enter the points. So I got my gradient. Since it's, when you do use 2 point, you use a gradient when it's a 2 variable function. Y equals, or 3 variables. Anything more than 1 variable, you use gradient. Anything less than 1 variable, you just derive, right? Just regular derivation. And so now what we do is we want our f of x, which is, we want to derive this in terms of x, that means treating y as a constant. And so we get 4. X derivative is just 1. Y, 3 is a constant, so it just stays. Plus my x derivative is 2x. Y is a constant, it stays. Comma. That's our f of x. Right? Now I gotta get my f at y, which is 3 times 4. So now we're deriving y and we're making x a constant. 3 times 4 is 12. My x is a constant, it stays, and then y becomes a power 2. Plus, this is a constant, and y goes to 1 when you derive it. Okay? And so this is that. So far, so good. Now what it's saying is find the maximum rate of change. So I know how I told you this by default will give you the maximum rate of change, just you gotta plug in 2 points. So what we'll do is plug in the 2 points. And what we'll get is 1 and 2 for negative 2 for y. So we get 4 negative 2 cubed plus 2, 1, negative 2, comma, and now 12, x would be 1, negative 2 squared, plus 1 squared. And now if we simplify this, what do we got? Negative 2 times negative 2, that's 4. 4 times 2, that's 8. 8 times 4, we have what? 16, 20, 32. If I got my math table right. Plus 2 times negative 2, that's negative 4. Right, so that's our x point, comma. Negative 2 squared is 4. 4 times 12, 24, 48. Plus 1. And so to simplify, this will be your 28, comma, 49. Cool. All right, so far so good for this part. I hope everybody is understanding it fairly well. I missed something here. This is a negative. When you cube it, it stays as a negative. So this actually turns into 32, 36, negative 36. All right, so far so good. So this right now does give us our maximum, right? But what this is in terms of x and y. And so if I draw this is my x. So actually, here I'll do it on the side. So I have my f at x and y equals to negative 36, comma, 49. Find my 49. All right. So my x now is negative. It goes this way. If I can make a better arrow. There you go. Right. And then my y goes up. Okay. So now I got my negative 36 and I got my 49. This is the magnitude of my rate of change. Right? This gives you an x and y, and if you want the actual value, you gotta do Pythag, which is pretty easy. You just do, your formula, which is y equals to the square root of 49 squared plus your negative 36. I don't know why I said 9 when I said 36. 36 squared. And that equals to the square root of 3697. All right, so far so good. But here, just to be clear, you gotta tell the notation wise, you gotta tell them what you're looking for. So what we would say here is we're looking at, so if we go back to our equation, we're looking at 1 and negative 2. And that would be your, even up here, you gotta say that my gradient at 1 and negative 2 is this values for x and y. All right, and so that's how you get your answer for a maximum rate of change. So when you do this, this is technically the answer, your maximum rate of change, right? But this is in terms of x and y. You want to turn it all into one component, and that's why you do Pythag. Now this one, I'm not going to go through it because this is, I'd be teaching English if I went through this. Look how much text there is in chemistry. So I'm not going to really go through this, but it's the same thing. You get some function, you get some points, you plug them in, you get the same thing. right? This one, however, says determine in which direction it moves. So you don't do your whole this step, because this gives you the magnitude. This gives you the direction. You see, when I tell somebody this is my rate of change, how do they know if I'm going this way, if I'm going this way, or if I'm going this way, or if I'm going, like, they don't know, right? But when you give them these, they can, from these, calculate my theta and get the actual angle. And so when I say direction, I'm asking just for these two, because these two give me direction. And so when you do this, it's asking for determining which direction, you give it just these. And if it asks a maximum rate of change, it's looking for an actual value. And that's when you give it a value. Okay? Now we're going into local maximum and minimums. It's the same thing we've been doing last Calc 1. And it's just you set a function to 0. There's a couple differences, and I'm not going to really go into this. I mean, you could read it if you'd like. I'm just going to go more into the concepts. And so it's telling you find the critical points of these of this function, which is a multivariable function. Now, how do you find your critical points in a multivariable function? Usually, in almost everything we've been doing in multiple variable functions, is we split them into two things: my derivative in terms of x and my derivative in terms of y. So we're going to do the same thing here. Get my derivative in terms of x, which equals, I'm going to derive all of this, right? But I'm going to treat y as a constant because I'm deriving in terms of x. So what I'll get is 3 times 3, which is 9, x squared, plus y to the 2, that's a constant, it goes to 0, minus 9x, that's just 9 when you derive it, and then plus 4y goes to 0. That's my first one. Let's simplify. 9x squared minus 9. You can pull out a 9 if you'd like. We'll keep it like this for now. And then I will also need my f at y. Now my 3x cubed is a constant, so 0, plus 2y minus 0 plus 4, which equals 2y plus 4. Now, how do you usually find your critical points from Calc 1? All you had to do was set the derivative to 0. Before, you didn't have to do it twice, because, it was f of x equals, x squared, then you derive it, and you'd get 2x equals your derivative. And if I want to find the critical point, I'll do 0 equals 2x, and then my critical point is 0 at x, right? And then you find your y, you can sub it in, you find your y and all that, okay? So in this part, we basically do the same thing. We're going to set this, we're just going to do it twice for x and y. So we're going to set this to 0 and find my x-intercept, my critical point. And so 0 equals, so actually I'll just do it up here, skip a step. 0 equals this, take 9 to the other side, right? Now what I'm going to do is take 9 and divide it. I'll get 1 equals x squared. Okay, now you'll have to obviously root, and so what you'll get is your plus and minus 1 equals your x, right? So whenever you root, you get a plus minus. Okay, so now here, same thing. Take 4 to the other side, negative 4 divided by 2 equals y, and then you'll get negative 2 equals your y. Okay, so the question is, now we found our critical points, what do? It's not only asking for local max or min, it's just asking for critical points. So you can say my critical, you know what? We're not doing this. This looks gibberish to me. See, my critical points are, right? And then you would do your 1, positive 1, and negative 2. And you would do your negative 1 and negative 2. So far, so good. So local min and max occur at critical points, but not all critical points. And what that means is, you see right at the point here, this is a critical point. This is where the change is 0. So you guys remember, local max is when your function goes up and it goes down, and like this, let's say. This is a local max. This is a local min. And you find it when your slope is 0. So you see the slope here is 0. That's why we set it to 0. So it's the same thing here, but you see, what if my function, you see in this case, or when I go like this in 2D, you see right here, this is 0, slope is 0, but this is not a local max or a min. So we have, it's the same thing here. So you see along this axis, right in the middle, it's flat, but it's not a local max or a min. And what we call it this is a saddle point. Okay? So these are the rules. This is given, right? And the rule says is if your D, this is how you get your D, by the way. You don't need to worry about this. This is vectors that looks like linear algebra. Don't worry about it right now. But your D, this is your D. You use this equation to get your D. And if your D is positive, then you can determine your local max and min from your f of x and f of, from your f double x. And if your D is negative, it's not local or max. This is a saddle point. Okay? If D equals 0, so you see none of this equals 0. If D equals 0, then the local slash your local max slash your min. Okay, so if D is 0, your local max slash min is inconclusive. Lol. All right, inconclusive. What this means is that at the certain point, not the whole thing is inconclusive. At the point that you're checking, at your AB, that you're checking that critical point, it's inconclusive. All right, and you have to check in some other ways that they're not teaching here. So if it's 0, just write inconclusive. So here they're asking us to find the local min and the local max and saddle points of a function. This is our function. So remember, the first thing to do is find our critical points. So f of x equals negative 3x squared plus y minus y goes to 1. And then I have my fy equals, this is 0. And then I'll get a x minus 2y. Okay, so we said now, remember, we said those to 0. So if I set this to 0, right, and I set this to 0, this is in terms of x and y. How will I get a value? You see up here, when I set it to 0, I got an actual hard value. But now I have a y. What can I do? One thing you can do is you can isolate for either y or x and sub it into the other. So I'm going to isolate this because this is easier to isolate than this. If I just take my y on this side, I isolate for x. Now I can take this and plug it in here. So I'll get 0 equals negative 3. My x is 2y squared, right? Plus y. Now everything in terms of y, I can find a point for y. Now, how can I find this? Let's expand. So I got negative 3 for y squared. I don't need this bracket here. So let's get rid of it. Just times plus y. And then what I'm going to say here is negative 12 y squared plus y. Now I'm going to pull a y out. And what I'll get is a y. Negative 12 y plus 1. All right. Now that I did all this, what I can do is isolate for y and find out. So I'm going to take these separate. You take this separately. So you do 0 equals y. So that's one critical point. And then I do 0 equals negative 12y plus 1. Take 1, negative 1 over negative 12 equals my y, which equals 1 over 12. Okay? So now we have two critical points. Okay? Which is, I have only found my y. So now what I could do is I could take this and sub it, these critical points. So I have y critical. I don't know why I keep writing critical. It takes so much space. YCP equals 0, 1 over 12. Now I'm going to take these and I'm going to sub them in here. Okay? So now what I'll get for my XCP now equals to 0, 1 over 12 times 2 is 2 over 12, which is, if I'm not mistaken, is 1 over 6, I think. Yeah, 1 over 6. 1 over 6. So now we have found our critical points, which are 0, comma 0, right? And your 1 over 6, comma 1 over 12. Okay? So that's, now the first step is done. I got my critical points. That was the most important part. Now what I gotta do is I gotta just use the equation that's already given up here to find my d. So let's do that. So I have d equals f double x. So now what I gotta do, I gotta get my second derivative of this. So f double x equals 3, negative 3, bring the 2 down, you get negative 6, nice, x plus y is a constant, it goes to 0. Now y equals, gotta grab this, x is a constant, it goes to 0, and then negative 2, when you derive it, you just get negative 2, right? And so what it's saying is, it's saying my first derivative of this x and this y, which is, right now I'm getting my d at 0, 0 critical point, so I'll specify that. D 0, 0. Yeah. Ooh. D at 0, 0 equals my f of x at these points, which is negative 6 at 0, because x is 0, right? And then times my f at y at these points, but you know I can't sub that in, so it's just a constant negative 2, minus my fx of y. So now I gotta get my fx of y. What is this? If I go here, I take this, and now I gotta differentiate this in terms of y. This whole thing is a constant. It will go to 0. My y will just be 1. Okay. So now I got a minus 1 squared. Okay, so what do I get? I get negative 6 times 0, which is 0, times negative 2, which is 0, minus 1. So this is negative 1. All right. Now my d at 1 over 6 and I'll zoom in. 1 over 12 equals to, I'll use my equation, which is f xx at this point, so negative 6 at 1 over 6 times my fyy, which is just negative 2, okay, minus my fyx, which is just 1 squared. Imagine if this had an y or this had an xy, you'll have to sub these points in. Just in this particular case, we don't. That's why it's not the case. But sometimes you do, and you gotta sub it in just like we're doing here. Okay? So what we'll get here is negative 1 times negative 2 minus 1, which equals 2 minus 1, which equals 1. All right? So what this says, all right, on the side, d at 0, 0 is lower than 0. Okay? And d at 1 over 6, comma, 1 over 12 is bigger than 0. Whenever your d is smaller than 0, by default, no matter what, anything else, by default, if it's this, it's a saddle point. Okay? Now your d 1 over x and 1 over 6 and 1 over 12 is a more than 0. So that tells us there's two possibilities. So it tells us, you see, if it's less than 0, it's not a local max, it's a saddle point. If it's one of these, you gotta go to the second round, which is now you gotta look for your fxx at the points you're looking for. So I'm gonna take this and sub my points. So now, since this is inconclusive, this is a saddle point, I'm done. Now I gotta check my f at x at my 1 over 6, comma 1 over 12. Okay, which equals my negative 6 times 1 over 6, which equals negative 1. Right? So if we go up here, actually we'll come back here. My negative 1 is lower than 0, which means my f(x() at my 1/6, comma 1/12 is lower than 0. If we go here, f(x() lower than 0 is a local max. Yeah, pay attention. If it's lower than 0, it's a local max. I know it's like meant to like, oh, if it's bigger than 0, that must be a max. It's bigger, but it's actually the opposite. If it's bigger than 0, it's a minimum. If it's lower than 0, it's a maximum. So because this is lower than 0, we can say our CP. So in conclusion, CP at 0, 0 is saddle point, and at 1/6 and 1/12 is max, local max. All right, and this would be your answer for it. So I hope that was pretty clear for you guys. Now we go to here, find the local maximum, minimum, and saddle points of this function. So I'm just gonna do this again, just for extra practice for you guys to see. I'm gonna do it on the side so it looks clean. All right, let me. How can I do this? Let me write it here first. So f at x y equals x to the 4 plus y to the 4 minus 4xy plus 1. All right. So what do we usually need, right? We will always need a couple things. I'll need my f of x, right, at some points. So I gotta first find these points. So first let's get our f of x, which is 4x cubed. This goes to 0. So minus 4y. That's the first one. And our f at y equals, this goes to 0. 4y to the 3 minus 4x. Right? Now you gotta set it to 0. 0 equals cubed minus 4y, and 0 equals 4y cubed minus 4x. And you see here, these are pretty similar, so it doesn't matter which one you isolate for, it works. I'm gonna go ahead and isolate for this one. So I get 4y equals 4x cubed. Right? Now I divide by 4, y equals x cubed. Now what I'm gonna take this, sub it in here. 0 equals, I'm gonna sub in, so I get 4x cubed minus 4x. Now I gotta find a way to isolate for all this stuff. So let's see what I can do. First, let me expand. Here I'll get 4x to the 9, if I'm not mistaken, minus 4x. Right? I'm gonna pull out a 4x. Right? So equals 4x, x to the 8 minus 1. There you go. Now what I'll do is isolate these. So I get 0 equals 4x, which is 0 equals x. That's CP of x 1. I'm not gonna write that because I feel like that'll confuse people actually. This is the first critical point of my x. And my second critical point, 0 equals x 8 minus 1. Then 1 equals x to the 8. Then if I root 1 by 8, I'll get a plus minus. And then so, I don't remember, do you only get plus minus when you square root a, what do you call it, by 2? Or do you get plus minus regardless what you square root by? Am I tripping? I might be tripping. No, I think yeah, you get. I was looking on the side to see if I was wrong, but that's fine. So far so good. We do actually get a plus minus. So plus 1, plus, oh my god. Plus minus 1. I can't believe I didn't know that. Lol. Okay. So now we have 3 critical points, which is 0, -1, and 1. Now we take those, we sub those in here. So y at 0 cubed equals 0. Y at -1 cubed equals -1. Y at 1 cubed equals 1. So our y is equal to 0, -1, and 1. Okay, so going down, what's your critical point? CP. CP, we have a couple now. We have 0, 0. We have -1, -1. And we have 1, 1. Now we gotta check all these, and we gotta get our D's. Now, before we get our D's, we know for our D equation up here, we know that we need a double X and a double Y, and we also need an X and a Y. So let's get those and make our life easier. Okay, so I'll do it to the side here, beside the already integrals. So if I do f x x, actually I feel like it would be better if I did it right under the fx, because so it follows. Move this. This is our CPs now. Okay, so now I'm doing fx. There you go. Oh no. Oh no. What's happening? There we go. Okay. So now we're gonna get our fxx equals 12 x to the power of 2 minus 4 goes to 0. That's done. And then we're gonna do the second one. I'm doing this just for clarity. I want you guys to be crystal clear with this. Alright, if you already know this, you can skip this whole part. But maybe if you stay, you learn something. So fyy equals 12y squared. This goes to 0. Now we also need my fxy, which equals to, by the way, you do want to put your x comma y here, but you don't have to. Well, I mean, technically on the test, yes, do, so you don't lose any marks. I'm just here saving time. So 12x squared, so I take this, and then I derive it in terms of y. This whole thing will go to 0, and then minus 4 is on my answer. All right, and so now what we're going to do is we're going to take this, and we're going to go up to my equation right here and sub it in. So I'm going to do this on the side. D at 0, 0 equals fxx, which is 12x squared. So how does it go? This equation is given. So this times this. So you go 12, 0 squared times my y's, which is 12y squared times 12y squared, and it's minus my fyx, yeah, fxy, which is -4 squared. Okay, so that's one. Let's write the second one. All right, so I'm just subbing stuff in. Nothing too crazy. And my d at -1 and -1, which equals 12, -1, 12, -1, and minus -4. Okay, and now when we simplify all these stuff, here we have this goes to 0, this goes to 0. This is -4 squared is 16, so this is -16. This one, 12 times 12 is 144. 144 minus 16 is, what do we got? 144 minus 16, that's 130. 128 equals 128. That's an ugly looking 8. Okay, and here we have 12 times 12 is 144. Again, this is a 1, 8. If I'm not mistaken. Yep. So now the next step is you look. If this is lower than 0, if your D is lower than 0, this is saddle point. Okay? If it's more than 0, then you want to look at your fxx. My fxx at this point, when you plug these points in, equals 12x squared. 12x squared. So what I'm going to say is my fxx at 1 and 1 equals to 12, 1 squared, which equals to 12. 12 is bigger than 0. Okay, so that's part 1. Part 2. here. This is bigger than 0. We're going to look for my x, right, at -1 and -1, which equals 12, -1 squared, which equals 12, right? And this is bigger than 0. Remember we said if this number is bigger than 0, it's the opposite. It's not big, it's not max, it's min. So, saddle point, this would be 12 bigger than 0, local minimum. It's opposite. So if it's bigger than 0, it's min. If it's less than 0, it's max. Minimum. And this one is also a local min. Make sense? So I hope you guys understood this, and I hope I have helped in your midterms. I wish you all the best, and good luck, have fun. I will be dropping maybe more videos for doing midterm questions, midterm practice questions.